Now we turn to the main topic of today's lecture, which is about Hilbert spaces. So here you have the pictures of two men, one of which you can guess is David Hilbert. So I'll give it to you right away. This is the picture on the left-hand side. And you might ask why there's another guy on this slide, and this other guy is no one but John von Neumann. And the reason that both are present on this slide is that, of course, David Hilbert introduced actually what we will call pre-Hilbert spaces. So it didn't really introduce the notion of completeness, which John von Neumann put to define what we could call modern Hilbert spaces. Roughly, what a Hilbert space is a generalization to infinite dimensions of Euclidean and Hermitian spaces, so which are vector spaces with an inner product, with a way to measure angles, if you like. And this is really John von Neumann on his treatise on quantum mechanics in the 40s, I think, who introduced, or 50s maybe, who introduced Hilbert spaces. If you don't know about this John von Neumann, I recommend you to read this. There is a nice article on the internet called The Unparalleled Genius of John von Neumann. It's easily accessible. And you will learn a bit more about this great mathematician, who's actually one of the great scientists of the 20th century and perhaps of history. So, the main topic then. For defining Hilbert spaces, we will need the definition for an inner product. So you're probably already aware of what an inner product is. Here, we just recall the definition and pay attention to the fact that this is a definition in C, so it's a complex valued mapping from H to H. So for now, H is just a vector space, so it's a C vector space, which means that the underlying field is the space of complex numbers. But it can be easily adapted to real-valued vector spaces, but for lots of reasons that we will see later, it's interesting to have the definition in C. So the first thing we asked for an inner product is to be linear. So be careful that this is linear with respect to the first variable here. Actually, it's not linear with respect to the second variable. Why? Because what we ask is that the inner product we ask the inner product to be Hermitian, which is the following property: that for any x and y in H, the scalar product of x and y is the conjugate. Okay, this bar here is the conjugate. It's the conjugate of y and x. Okay, which means, for instance, let me write this, tell you what this is not linear in the second variable. In general, that means that, for instance, if I want to compute x and lambda, so lambda is a complex number, lambda y, well, by assumption, I only have linearity with respect to the first variable. So what I need to do is use the Hermitian property, which tells me that this is lambda y x, but this is a complement of lambda y x. Then I can use the linearity, the first property, which tells me that this product here is lambda bar times yx bar, which now I can use again the Hermitian property is lambda bar xy. So you observe that I do not have linearity, because if I had linearity I would have lambda here, but instead I have lambda bar. So now if you work in a real valued vector space with a real valued inner product, then of course that means that you chose lambda here to be real, so lambda bar is real as well, and then you get linearity in both variables. But in C you have to be careful. And the last property that we ask for the inner product is that it's positive definite. So this property says that for any H in my vector space, the inner product of x against itself is non-negative. And the fact that it's definite means that if this inner product is 0, if and only if x itself is equal to 0. Okay. So, like I said, if RH is an R, it's a real valued vector space, then the inner product is a mapping from H to H, from H times H to R, sorry, and it's linear in both variables. So yeah, perhaps let me give you a simple example of a scalar product and infinite dimension, because this covers, of course, inner products in finite dimensions as well. So example, so I will give you the usual scalar product. So let's say we are in RD or in CD, if you prefer. Well, the usual scalar product is the following. It's given like that, x, y, which is equal to the sum of the xi, yi bar for I equals from 1 to d. Right. Now, some properties, of the inner product. Well, the inner product will give us a norm as follows. So if you define x, to be the square root of the inner product of x against itself, then this defines a norm, and that's what we will call the Hilbert norm later. So just quickly, why is this a norm? Well, proof. You'll see that it's quite straightforward. So say homogeneity first. Okay, so let lambda in R. So perhaps I can do that for C. So let lambda in C and x in H. Then lambda x. So by definition, this is the square root of lambda x against lambda x. So I will use the linearity. This gives me square root of lambda of x against lambda x. Then use the Hermitian property, which tells me that this is equal to the square root of lambda times, and then use again the linearity. So it's lambda bar. We've done that just before. X. Okay, and lambda times lambda bar is the modulus of lambda squared. So this is equal to the modulus of lambda times the square root of x times x, which is equal to the modulus of lambda x squared. Oh, sorry, so there's no square here because I took the square root. Fine. So I have the homogeneity. Then I want to prove that if the norm of x is equal to 0 if and only if x is equal to 0, which is the separability property of the norm. So let x be in H. So from the positive, we will use the positive definiteness of the inner product. So we see that norm of x is equal to 0 if and only if the inner product of x against itself is equal to 0, which is equivalent, according to this property, the positive definiteness, it's equivalent to saying that x is equal to 0. So this mapping is separating. And the third point is the triangle inequality, and I will not prove it now. Okay, so later, using the Cauchy-Schwarz inequality. Okay, so we have a norm, which is given by the scalar product, by the inner product. So now that we have a vector space and an inner product, and a norm actually, we can define what is called a pre-Hilbert space, which is nothing but a vector space with an inner product. Okay, so I will give examples right away, but first let me give you another definition. And there are numerous reasons for which we want spaces which are complete. I already mentioned some of them, but this will be again more true here. For instance, if we want to be able to talk about orthonormal bases, the existence of orthonormal bases, it will be very important that our space is complete. Some other reasons, like if we want to compute projections on subvector spaces. So we had this definition. The reason why we call the first one a pre-Hilbert space and not a Hilbert space is that a Hilbert space has to be complete. So pre-Hilbert space that is complete is a Hilbert space. So, for instance, examples. So again, I will start with the finite dimensional standard example. So let's say RD or CD. Okay, I gave you the inner product earlier. And in fact, well, the norm associated to it, so remember, okay, the Euclidean, what we call the Euclidean scalar product is this. Or Hermitian, sometimes we say Hermitian when it's complex. Let's say Euclidean is equal to the sum of the xi, yi bar, and the norm associated to this is sum, so square root of sum of xi, so the modulus squared for I equals 1 to d, and RD or CD with this distance, with this norm, okay, is a Hilbert space. So it's a finite dimensional one, but it's still a Hilbert space, so it's complete in particular. Okay, so that's the first example. Let me go to a bit more difficult one in infinite dimensions. So we will consider the space of sequences L0 of n. Okay, so the set of sequences U which takes value in C, for instance, such that U takes finitely, sorry, can I say that? Takes only finitely many non-zero values. Okay. Okay, this means that U is in L0 of n if and only if there exists n rank, after which for any n greater than n, un is equal to 0. That's my definition. Well, I can put an inner product on this, for instance. Let's take two sequences, U and V in L0 of n, U and V, and define this inner product, sum for n in n of U n V n bar. Well, check that, so of course check that L0 of n is indeed a C vector space. Check that this is a scalar product. Okay. And in fact, what you can do, so I will give you an example, I will give you a way to do it, but check that L0 of n is not complete. So of course, complete for the distance or the norm induced by this inner product is not complete. So you could use the following sequence. So if you want to prove that some space is not complete, then what you do is that you try to find a Cauchy sequence which does not converge. So what you can do is take this sequence. So for instance, so that will be a sequence of elements in L0 of n. So that's a sequence of sequences. So for instance, prove that. Let me give you this sequence UM. Okay, so UM for m in n. this is a sequence which takes values in L0 of n, okay, defined as, so just an example, because there are plenty of others, but defined as, so um at rank n equals to, let's say, 1 over n if n is smaller than m, and 0 if n is greater than m. Okay, well, so prove that this sequence defined is Cauchy, the Cauchy sequence, but in fact you can also see that the limit is not in L0 of n, because there are more and more in as m becomes larger, there are more and more terms which are non-zero, and in the end it's no longer in L0 of n. So I had a quiz also for you, so maybe quiz if you like. So we will work on R with the following distance, or with the following mapping, say, on R with delta, okay, it goes from R times R to R, say, defined as, so delta of x, y, which is equal to 1 if x is equal to y, 0 otherwise. So this is a mapping from R times R to R. And so question 1 is delta a distance? Question 2 is, if yes, sorry, let's say, if this is a distance, is R with delta complete? And the third question, if yes, so if this is complete, is R with this norm that I normed the delta norm here, a Hilbert space, where this thing here, sorry, so I define this object, I mean this object, I'm not saying that this is a norm, this is for you to check. This object defined as delta of 0x, okay, so is this a Hilbert space? Okay, the question first, is this a norm? So here's your little quiz. Right, so here again you have the previous example, L0 of n, with the inner product that I introduced before. Like I told you, this is not a complete space, and its completion is actually this space, L2 of n. And you have an exercise, I think it's exercise 2.5, where you have to prove that this is indeed a complete space. So this is then a Hilbert space for this inner product, right? And later we will work a lot with this space. Okay, so for now it makes no sense. This is a Lebesgue measure, this is a Lebesgue integral, so we will see that in great details later. But we will see spaces of functions, of square integrable functions with this scalar product, which will turn out to be Hilbert spaces. Later also during, for instance, the PDE course, you will meet the Sobolev space W12, okay, which sometimes is called also H1. So we'll see that Hilbert spaces are really common thing and very very useful framework to work with. For instance, this is the case in quantum physics. All of quantum physics is built upon Hilbert spaces. And now some properties of the scalar product and the norm, the Hilbertian norm. So in fact, probably you know all of these properties already. So perhaps I will skip their proof, or at least partially, since these properties are already true in finite dimensions. So for instance, you have the Pythagoras property. So it's just slightly more general than what you're used to write for triangles, because here we have the angle that appears here. So it's not the normalized angle, but this does measure the angle between x and y. So of course, when x and y are perpendicular, when they are orthogonal, then you recover the usual Pythagoras identity. The Cauchy-Schwarz inequality, okay, which will be very useful. We will use it a lot. The Minkowski inequality, which derives from the Cauchy-Schwarz inequality. You have also the parallelogram identity. So I write this one because I will use it in one of my proofs in a few minutes. And this one, which is called the polarization identity, which is nice also because you see that in fact, if you only know, sorry, the norm, if I read it from right to left, okay, then I see that to have the value of my inner product, I only need to know the values of the norms. So the first one I will not prove because it's quite straightforward. You just develop this. Okay, the Cauchy-Schwarz inequality is actually the only one that I will prove, because otherwise the other ones are all derived from computations. Okay, so proof of Cauchy-Schwarz. So this goes as follows. It's quite simple, but it's tricky. So let's say I define P of t, which is the norm of x plus ty squared, and I will define also t0, which is minus the inner product of x and y divided by the norm of y squared. Then what we know is that P of t is non-negative, of course, this is norm. And so we know that P of t is non-negative, and this thing here actually is what? It's the norm of x minus xy y over y squared. Okay, squared. Okay, and if I develop this, okay, so you develop this, and actually this is equal to x squared plus xy squared minus 2 times 2 times xy squared over y squared. Okay, so now what do I deduce from that? Well, this is non-negative, like I said. Then this implies that, yes, this was divided by y squared. Here, better. And now that I've done that, well, I see that I can multiply all this by the norm of y squared, and then what I get is exactly what I wanted, that is xy squared, which is less than x squared y squared. Okay, and then I take the square root and I obtain my Cauchy-Schwarz inequality here. Okay.